Swayam Prabha. Digital India. Educated India.
Hi everybody, this is Akshaya, a third year undergraduate in the Department of Chemical Engineering. So under the course of Sustainable Plastics, the project I've chosen is development of sustainable oil-based polyurethane films, particularly the porous kinds, and we are doing the synthesis and characterization here. So I specifically chosen castor oil as the synthetic oil which I'm using. The reason being that it's not a food grade crop, so it's not going to be competing for those. And then there is also the fact that it's a triglyceride, and it kind of has a very long fatty acid chain which can improve the flexibility of the polymer which we generate. So there are two kinds of characterizations which I have primarily done. One is the FTIR and the other is the SEM. So FTIR is basically used to identify the functional group which is present, and the scanning electron microscope just tells us about the structure of the polymer which we have created. So I've tried two major methodologies here. One is via transesterification and then creating a polyol, and the other is directly forming the PU film. So starting with the first methodology, we kind of convert castor oil into a monoglyceride by reacting it with glycerol under suitable conditions of nitrogen and temperature of 220 degrees Celsius. And then we react it with phthalic anhydride to form the polyol. But then the FTIR result for the polyol, it did not show any significant improvement in the number of hydroxyl groups. So the reason being there is no stability which it finds, and then there is already hydroxyl group present which doesn't enable further addition. So we moved to the second method. So it was kind of using diol and diisocyanide to form the pre-polymer, and using castor oil as a cross-linking agent to form the PU film. So this is the PU film which we kind of got. And then this is the FTIR result for the PU film, which kind of shows the NH and CO peaks. And this is the SEM images which we kind of find. So there are these micropores which are found, and then regions of local soft regions, and there are very minimal number of hard regions which are found here. So all these prove to flexibility of the polymer, and we kind of concluded the experiment there. But then it can be further extended because this is quite a large area where we have a lot of applications for microporous films, particularly food grade applications, biomedical applications like tissue engineering, and so on. So yeah, that's where I would like to end, and I would like to thank Professor Ethayaraja and my guide Dilip Kumar for providing me with this opportunity to perform this experiment. Thank you.
Hi, I'm Rojita, a third year chemical engineering student from IIT Madras. As part of the sustainable plastic course, we have chosen a project, and that is extraction of I have chosen extraction of chitin from edible mushrooms. Chitin is the second most abundant polymer after cellulose. It is also biodegradable, biocompatible, and also it is non-toxic. Traditionally, chitin is extracted from crustaceans shells like crabs, shrimps, and also it is present in exoskeleton of the crustacean shells. But this process involves it is complex, and it generates a lot of waste, and it is like allergic reactions also. So to come up with the other option, like in a sustainable manner, in eco-friendly manner, we have mushroom. We can extract chitin from mushrooms. First we chopped the mushrooms, and then we oven dried the chopped mushrooms, and we got the powdered mushroom. We treated the powdered mushroom with NaOH, where we removed this process is deproteinization process, where we removed the alkali insoluble matter, where we got the alkali insoluble matter which chitin present in this, and there is other insoluble materials like protein, lipids, and other biomolecules. And we oven dried the alkali insoluble matter, and then we isolated the chitin using the acidic treatment with acetic acid, where we got the pure chitin. To know whether we got the pure chitin or not, we did some categorization like SEM, XRD, and FTIR. Coming to SEM, we got a very fibrous and porous structure, and also which confirms the presence of the chitin, and also we got very irregular and clean and minimal surface debris where we can see the removal of the impurities from the matter, like where we can see we got the successful removal of the non-chitin components from the during extraction. And also from the XRD we got peaks like around 10 degrees and 20 degrees where the where we can confirm the alpha chitin, and also the crystallinity is lower than the commercial like where the chitin extracted from mushroom, the crystallinity is lower than the commercial chitin. And also from the FTR analysis where we can see major peaks like around 1000 to 1200 where we can see the bonds like CO and CH, and also we can see major peaks confirms the OH and NH bonds and also amide bonds. And we can also see the absence of the protein bonds where we can we remove the proteins in this process, so we can confirm that we got the without protein bonds. And also we can conclude from this that mushroom can be an alternative way to extract the chitin, and it's a sustainable way to extract the chitin. And also this method we can also reduce the waste of we can also reduce the using of dependence on the crustacean waste. And I would like to conclude it. And I would like to thank my professor Ethayaraja sir and also my mentor Hemakumar, and this is a rare opportunity to do an hands-on experience. So thank you so much.
Hello, I'm Sakshi Talpade, 4th year chemical engineering BTech student, and my topic for the project is extraction of cellulose from bunchgrass Chrysophogon zizonians, also commonly known as vetiver. We all know that we are overly relied on petroleum based plastics and the problems they cause to the environment. So hence the biocomposites are a better way to replace them, and Chrysophogon zizonians, that is vetiver. Vetiver is usually used for extracting oil, but after extracting oil from the vetiver, the roots are basically termed as agro waste, which is not much used further. But this waste roots are full of cellulose, hemicellulose and lignin. Here cellulose is found in major quantities, so this cellulose can be used as fillers or reinforcement in biocomposites, which are like thermoplastic starch based biocomposites. So hence my objective here was to extract pure cellulose from these roots through a two-step chemical process, delignification and alkali extraction, and also to verify it with FTIR spectroscopy that lignin and hemicellulose is removed. So I had first mixed a vetiver sawdust with water and heated it at 80 degrees Celsius, and then added sodium chloride along with acetic acid to which basically carries out the delignification. It removes lignin from the biomass, and then the resulted product is then filtered and washed and oven dried overnight. So we obtain hollow cellulose, which is hemicellulose plus cellulose. Then this hemicellulose is treated with NaOH solution for 2 hours, and then 2 hours to remove hemicellulose from the biomass. And then the final product is again filtered and washed with diluted NaOH, water, acetic acid and acetone, and then the filtered product is oven dried overnight to obtain pure cellulose. Now we can verify the results with the FTIR spectroscopy that we had. So here the lignin and the hemicellulose peaks are absent, which means that we have completely removed lignin and hemicellulose from the biomass, thus giving us pure form of cellulose. Also the signature peaks of cellulose are evident, as we could see the peak absorption band of OH and the COC backbone peak. So hence we can verify that pure cellulose was extracted, and the lignin and hemicellulose was completely removed from the process. Overall, this study shows us that vetiver agro waste is not actually waste. It's a very low cost and abundant source of pure cellulose, which can be extracted and then can be used in thermoplastic starch-based biocomposites, which is again a key in building sustainable plastics. And yeah, lastly, I would thank Ethya sir to give me an opportunity to actually work on this project as a part of my course Sustainable Plastics, and also Induja ma'am to my student guide to guide me throughout the process. Thank you.
Hello everyone, I am Chiran. I am a final year undergraduate student from the Department of Chemical Engineering. I would like to present my work on 3D printing of biopolymers as part of my course project. The motivation behind choosing this lies in the fact that there is a growing need for sustainable, customizable and especially biocompatible and biodegradable materials in the field of tissue engineering and other biomedical applications. And I always had a genuine interest in additive manufacturing since 2 to 3 years. So I have chosen this concept. My objective as a part of this was to evaluate the suitability of polyurethane for 3D printing and determine the suitable conditions and parameters in which this is possible. As a part of this, I also have worked with different polymers such as PLA, polylactic acid, PCl, polycaprolactone, and this work, the printing which I have done is now with the help of polyurethane. PU is a polymer which has carbamate linkages between diisocyanates and diols. The methodology involved goes as this. The solvent I have used is DMF here, but for the different polymers I have worked with different solvents such as chloroform and others. For this, as far as PU is concerned, the polyurethane crystals have to be dissolved in a DMF solution and stirred using a magnetic stirrer at 60 to 70 degrees centigrade at an RPM of 400 to 450 RPM for 1.5 hours to 2 hours. I had started with 5% concentration solution. Then we have to slowly increase the concentration till we obtain the suitable consistency. I had tried with 5%, 10%, then increased to 15%, 20%, and at 20% consistency, at 20% concentration, the gel seemed to be of suitable consistency. But when it was loaded in and tried to be printed, it was getting solidified instantly. So, which shows that it was not a suitable formula. Then I had to increase the concentration beyond 20%, and finally we arrived at a suitable consistency and characteristic of the gel, which can be printed using a bioprinter. These are the structures which I have tried to print using the gel that I have prepared. Moving on, if I have to talk about the applications, these, especially the polyurethane 3D printed structures, have a wide variety of applications in tissue scaffolds, in automotive parts, etc. This is just the fundamental and the first step of this process. This can be improved to different levels by trying composite solutions with different polymers. This is, we can try with multi-layered printing and increase the thickness of the structure and evaluate its behavior in a biological environment, perform degradability test and biocompatibility test, and if it's found suitable, then it can be a potential applicant for tissue engineering applications as well. So we can see that PU was a good choice for this 3D printing activity. I would like to thank my mentors Dilip sir and Aishwarya ma'am for the continuous help in this work, and I thank Professor Ethayaraja for giving this chance. I really enjoyed this work. This project really changed the way I looked at research work, because before this project, research was like, I used to think it's not so difficult or it's a straightforward thing which is to be done. But until we get into lab and see, we find the difference between what is given in the paper and what we have to do, we might not find everything suitable for us. So that's a great learning in this work. I encourage to explore this field. Thank you.
Hi and good morning everyone. I'm Mohna Priya, a PhD student under Professor Ethayaraja Mani. My study is on faba bean protein based foam. So faba bean is a rich source of protein with a protein percentage of 30%, and the main protein percentage of this faba bean is viscellin and legumin. So the reason why I took faba bean is simply out of curiosity. Why can't we extract protein? There are a lot of protein which is already available in market. Why can't we extract protein from faba bean too. So, and I gone through the literature, and I found that it has good protein sources, and also it has good favorable property, which is what I want for my protein foams. So yeah, this has some methodology. First, protein extraction, and then foam formation. First, I sourced the faba bean and dried it in 50 degrees Celsius for overnight, and then I grounded the faba bean into a flour, and then I dispersed in a water and I adjusted the pH using NaOH to make the protein soluble in water. And after this, I centrifuged it and collected the supernatant. After collecting the supernatant, I acidified it to make the protein, that is visumin and legumin, in the to make it agglomerates. I acidified it. After acidifying, I stirred it for half an hour to make the precipitate. And after precipitating it, I centrifuged it to collect the precipitate. And I collected it and resuspended it in water to purify the protein. And after dispersing it in water, I again centrifuged it to collect the base protein. And I did adjusted the pH to make it stable when we are drying. So I adjusted the pH to 8 to make it like slight basic, and then I dried it in 35 degrees Celsius under hotter oven, and I scraped the protein and I got the protein. And after this, I did foam formation. And for foam formation, I dispersed the water. I dispersed it protein in water, 100 ml water, and I added fillers like xanthan gum and additives like SDS and the CMC to make it more. SDS is added to make foam and to enhance the foam, and the additive like CMC is added to enhance the structural integrity of the foam. I homogenized it. I stirred it for 15 minutes under high RPM, that is around 2000 RPM, and I formed a foam, and I dried it in both drying. One is oven drying and another one is lyophilization. I dried both process, and I got the foam. And these are the characterization technique. FTIR is for proving it is the extracted protein is protein, and it has a few peaks. One is amide 1, amide 2 and amide 3. All these are present in protein, which proves it as a protein. And XRD diffraction, this has some broad peak around 19.68 degree, which shows it is amorphous, not crystalline. And I took same morphology for the foam, which says it has pores with the cracked feet, because have to make pores. So then I conclude here that this alkylation method is efficient for protein extraction from faba bean, and the resulting protein is also exhibiting a very good foam formability. So hereby I conclude that it is a very good source for protein foam, and future work will be optimizing the protein concentration, like optimizing the protein concentration to form the foam, and adding some formulated additives to enhance the structural firmness of the foam. Thank you.
I am Gokul Shankar. I am a PhD scholar from the Department of Chemical Engineering, IIT Madras. I am working with Professor Ethayaraja. As my part of my coursework, Sustainable Plastics, I chosen the research problem, thermoplasticized pectin for compression and extrusion. So, biopolymers are an emerging field for sustainable alternatives when compared to conventional plastics. So, however, the biopolymers, since there is an unmet need for an industrial processing. So, in my work, the objective is to formulate the thermoplasticized pectin with addition of natural deep-reductive solvent and the glycerol. And the second objective to reduce the caramelization and enhance the milk flow behavior to process the flow. So, we chosen biopolymer as a pectin. It's a naturally biodegradable polymer, and it is sourced from fruit peel waste, and it is biodegradable, cost effective, and it is sustainable for food packaging applications. So HFP is degrade, and it's not thermally stable and caramelized during high temperature. So for this we have to add NATs and natural deep reductive solvents and glycerol as a plasticizer. So coming to a methodology, first we have taken high methoxypectin and NATs and glycerol solution. So complete mixing with stirrer, and according to our end application, we have designed a mold and formulated this material filled up with this mold, and thermally compression the mold with in 110 degrees Celsius, the end product will come. So after this, this has been cut into small particles to extrude. So we done thermal compression as well as extrusion process. So we have to study how the polymer will melt flow in that extrusion process. In the extrusion process, I tried with two kind of experiments. First thing is a single screw extruder. So in the single screw extruder, the material will clog inside the screw. The temperature is not uniformly distributed. So the material clogged and char in between the extruder. So I have tried with the injection molding. Maybe if we try with a twin screw extruder, there has a temperature zones. So we'll control the temperature. So it may be extruded in the twin screw extruder. So as the second experiment, we tried with the injection molding. In the injection molding, the polymer will get melt and flow will get very good flow. So during injection molding, we get an inline filament, and also this filament has been cut into small pellets. So again, we can using these pellets, we can try it on a mold, and this will be a cycle process. We can, whatever product we want, we can make a pellet, and based on this we can have the material. So for results and discussion, we did a canal analysis. So the first two material represents without natural deep reductive solvents. So these natural deep reductive solvents will reduce the caramelization. So the technical reason was the natural deep reductive solvents has a strong hydrogen intermolecular bond. So it will reduce the oxidation process involving during the glycosidic bonds. It reduces the caramelization. So the third sample represents the NATS, incorporating the NATS sample. So we can see the significant color difference including NATS and without including NATS. So coming to an FTR analysis, we done for a pure pectin and a filament pectin. For comparison, there is no significant molecular difference in filament and pectin. So these peaks corresponds to the pectin molecules. The first peaks represents OH bond and CH stretch, and these are the peaks represents the glycosidic bonds. So then thermogravimetric analysis, we compared with the pectin as well as the extruded pectin. So both the cases we had weight losses are to 3 stages. The first stage represents the weight loss of moisture content and glycerol. The second prominent peaks represents the pectin degradation, and the third one is a ash content. Up to 300 it will get charred. So when compared to the pure pectin and extruded pectin, it shows the similar significant difference. This pure pectin shows a 210 degrees Celsius and the extruded pectin is a 228. It's a slight thermally stable when compared to that original pectin. So finally, I want to conclude will formulated pellets to enhance the thermal stability and minimize the caramelization process, not only reducing the caramelization process, and also it will improve the melt flow process. So then this work provides sustainable prototype to develop a biopolymer based materials by using the existing polymer based extrusion techniques like compression molding and thermal compression and extruder. So I want to thank my guide, Professor Ethayaraja, and I'm very special thanks to Chidambaram. So he helps me to do lots of things in the mechanical department to mold the product and to design a mold and everything. So I want to thank Anoga Manogar to complete this project, morally support she as we planned. So I want to thank all my lab members to complete this project, and thank you. So I want to conclude, we formulated a material so that not only reduce the decaramelization, and also it will enhance the thermal stability and improve the material processing capabilities. And this is a promising sustainable alternative, the prototype to develop biodegradable materials with the existing facilities like extrusion or compression methods. And I want to thankful for my professor Ethayaraja for organizing this course to learn practical experience with courseworks. And I want to special thanks to Chidambaram to help me out reach that designing the mold and extrusion and compression. And I want to thank Anaga. She supports me morally to complete this project as we planned. So thanks to my lab members and classmates. Thank you.
Hi everyone, this is Ananya Munangi, PhD scholar under the guidance of Professor Sumesh P. Thambi. Today I have done a project on chitosan and wax coating as an alternative to multi-layer packaging. So I have coated the chitosan and wax on the paper. So this is the methodology. I prepared the chitosan solution of 3 different concentrations, 2%, 4% and 6%, and then coated a thin layer of carnauba wax on the dried chitosan coatings using a continuous casting machine. So these are the results. So this is the 2%, 4% and 6% chitosan coating, and the below are the respective wax coatings. And I have also coated the plain paper with a thin and thick layer of wax. You can see this. And the thick layer of wax was breaking and peeling off. And the paper also lost the flexibility when I coated the paper with a thick coating of wax. And I've also tested for the hydrophobicity, the contact angles. So the paper, I used a 300 GSM paper so that the water doesn't soak the paper too much. And the contact angle of the paper was around 90 degrees, and for the 2%, 4% and 6% chitosan coating, the contact angle increased by 10 degrees. So the contact angle was around 101 and 102 degrees. And I also tested for the contact angle of the wax coating over the chitosan coatings, and the contact angle difference was very less, around 1 degrees. And the thin and thick wax coating showed a considerable contact angle increase. The thin coating was around 115 and 120, while the 115 and the thick wax coating was around 125 to 130. And the bending of the paper when I coated with the thick wax coating interested me to see how the paper bends and forms shapes when I put different patterns on the paper. So I used 2 different wax, a carnauba wax and candle wax, to do the strip coating. So these are the samples of strip coating. This is a thin layer of carnauba wax and this is a thicker layer. So, and for the strip coating, continuous casting machine is not the thing. And if you see, when the space between the 2 strips was less, the curvature was more, while when the space between the strips was high, it was almost flat. And candle wax was not suitable for this experiment, because the candle wax, even with the both thick and thin coating, it was either seeping into the paper or it was just chipping off. So as a conclusion, I would say that 4% chitosan solution was giving a uniform coating, while the 2% chitosan solution was soaking the paper even if it was thick, and the 6% was forming a gel formation, so the coating was not uniform. And with the wax, I used just wax alone, so it had wettability issues, and even the carnauba wax was, even the thin layers were peeling off after a considerable amount of time. So for the wax, I would suggest to go with emulsions or polymer blends. And I would like to thank Professor Ethayaraja for giving this opportunity as a hands-on experience for the experiments along with the coursework. And I thank my peers for their help in my experiments and for their moral support. Thank you.
Hi, I am Reshma. I am working as a junior research fellow under Professor Ethayaraja. We all know that polymers are indispensable to mankind nowadays. From the t-shirt we are wearing to the food products we are storing, that also contain or made up of plastics. So why? Because plastics are using all applications because of the durability. Now I am going to talk about other side of this coin. Actually, this durability is actually making the crisis that we are facing nowadays. So that is why important to make a sustainable packaging. So I'm very grateful for Professor Ethayaraja for giving an opportunity to learn about sustainable plastic from this course. So let's dive into my work. So I chose siloglucan. So why? Because siloglucan, it has a bioadhesive property to bind the cellulose fibrils. So it has helped to the structure integrity for the cell walls in all plants. So I incorporated this strategy into make a bioengineered product. Here I have chose tamarind kernel powder to make my siloglucan. So I extracted it from the seeds and I have incorporated it with ethanol and I have made the gels and I dried the powder. Then I got the siloglucan. So how do we know I got the exact stuff? So I do perform the FTIR. From that, here the 1042 peaks and the 896 peaks are composed of that depicts exactly the glycosidic peaks. So then I incorporated this strategy into my 3D printed siloglucan wood composite. Here I used direct in writing 3D printer. This is exactly the siloglucan itself. It has good structure property along the siloglucan. Then I have incorporated microcrystalline cellulose and also some sodium arsenate for the rheological property and also my wood particles. So here we can see the dimensional fidelity is very stable. It doesn't even dispersed, like it not spreaded. Then also I have used this strategy to make a composite also. Here we have used PLA, siloglucan and also wood. The wood is exactly the Devadaru wood. Actually it will use for Ayurvedic medicines because of the antimicrobial properties. So my final product I am choose for a cosmetic packaging. So I mixed with PLA, siloglucan and this wood particles. For that I have used twin screw extruder to grind like compound the material. Then I extruded it, then pelletized it. Then I used a compression molding to make these two specimens. Actually these specimens are very good, it's very strong. Here you can see my specimen. In future I am gonna use an XG means siloglucan wood rich composite for cosmetic applications. And also I am very thankful for Dr. Ethayaraja Das for helping me to choose this siloglucan material, and also Dilip Kumar as for making this 3D printed structure, and also for Dr. Chidambaram for helping me to make a 3D thermation molded composite. Thank you.
Good afternoon everyone. I am Aniket Tiwari, a final year undergraduate student in the Department of Chemical Engineering at IIT Madras. Today I am going to showcase my project that I did in the course Sustainable Plastics under the Professor Ethayaraja and my guide Ananti Pandey. So basically my project title was to understand the grapeseed waste phenolics for antioxidant packaging applications. Why I chose to study and do the project on this topic was because we see that there are a lot of food spoilage and plastic waste because of the traditional packaging material, and so I chose to work on grapeseed extract, which is very rich in polyphenols, which acts as antimicrobial and antioxidant compound. The objective of this experiment was to do the solid liquid extraction for grapeseed extract and study the characterization results through Fourier transform infrared spectroscopy, that is FTIR, and DPPH assay reagent, and other XRD as well as SEM analysis. So as I have already mentioned, I chose grapeseed because it is rich in polyphenols, which acts as antioxidant. I'll go through the procedure that I followed. Basically, I ate 1 kg of grape for 2 days to collect grapeseed from it, and then I dried it in the oven for 3 hours, converted it in fine powder using grinding machine present in the lab. Then I made the solution by taking 2 grams of seed powder and added to 20 ml of aqueous ethanol, 80% by volume. And then I centrifuged and collect the supernatant, which was dried for 3 hours again. I got the a powder form, dried powder form of grapeseed, which was used as FTIR XRD SEM analysis. So I'll go through the results. From SEM analysis, we can see that it's a rough and very porous morphology that shows that it has a nice solvent penetration, shows polyphenol extraction efficiency as well. XRD result shows the peak around 20 to 25 degrees Celsius, which confirms it's a very diffuse peak, so we can say that it has a better solubility as well as uniform film integration. The FTIR result, from FTIR graph we can deduce that it contains hydroxyl group as well as aromatic rings are present in the grapeseed extract. And at last I performed DPPH assay reaction to confirm the antioxidant capacity, which turned out to be 74%. So yeah, it was a very nice and fun experiment. I got to eat so many grapes initially to collect the seeds, and I liked the exposure that I got while working in the lab, because I was never involved in any such activity before. I went to a CHL and did many course lab, but this was very unique, and I got to learn a lot from Dr. Ananti Pandey ma'am as well as Ethayaraja sir. Yeah, thank you very much for this opportunity.
Hi everyone, I am Aishan Pala, final year student in chemical engineering at IIT Madras. So my project is starch-based bioplastic films. So I choose this project because conventional resources like plastic, which were derived from fossil resources, were causing a lot of environmental damage. But bioplastics gives us a way in which we can make biodegradable plastic. So the aim of this project is to make simple biodegradable plastic and study the impact, study the how amount of glycerol affect its properties. Okay, so I choose the corn as a biomass, and I extracted starch from it by washing, blending it with water, and after that the starch is extracted. I prepared a starch slurry and heated it up to 60 to 70 degrees Celsius. And so at this temperature the starch granule swells, gelatinizes, and it further releases amylose, which is essential for forming polymer networks. And after that the starch is formed. I dried it, so I left it for drying for some time, and after that I added glycerol in it. Glycerol acts as a plasticizer, which helps in reducing the intermolecular forces between the starch granules. And after that glycerol is added. I have added various concentration of glycerol in it, so that I can get various sample and I can study the impact of glycerol in the properties of this bioplastic. Okay, so after that this hot gelatinized paste is further poured into the plastic film, plastic glass as a thin layer, and it is left for drying for 12 to 24 hours overnight. And after that it is dried, I performed some physical properties test like film thickness, moisture content, and film solubility, and further water absorption. So as the result you can see that as we increase the amount of glycerol, the solubility also increases, and water absorption as well as the moisture content also increases in the bioplastic. It is because glycerol is hydrophilic in nature, and it reduces the crystallinity of the starch. Okay, so after that I also performed some mechanical properties tests like FTIR, which confirms the starch glycerol interaction, and it shows the characteristic OH and CO bond, which confirms the correct film formation. So overall, starch is a biodegradable and a renewable resource for making bioplastic, and it can be further extended by it. Future improvements can also be done by adding biopolymers as well as further fibers, which can make it more better. So the only drawback in this was it was moisture sensitive and lower in strength, which may cause some limitation as it can be used in small life packaging applications. So yeah, I want to thank Mr. Ethayaraja sir, Professor Ethayaraja sir, and it was a wonderful course, and I really learned new things about bioplastics, and thank you.
Hi, good afternoon. I'm Kunal Panda, and I did protein extraction using DES. Now, first of all, huge thanks to Professor Ethayaraja, because this is a very rare opportunity, and to work at a lab in IIT Madras, and it was something of which I really appreciate. And in my project I'm using flax seeds. So as we know, flax seeds is very rich in protein. It is like 40% protein, and we can say it is also very oil rich. So, and that is the reason why we had to defat it, because we don't want it to interfere with the protein extraction. So we used hexane to remove the fat. We used it in 1:5 ratio of seeds to hexane, and then the supernatant, actually it extracted all the oil from flax seeds. We repeated the process 3 times. After that, we proceeded with protein extraction. So the DS we used was choline chloride and glycerol in 1:2 ratio. Now you might be asking, why DES? There are a lot of reasons. First of all, DES is completely biodegradable, and it has a pH which is between 5 to 8, so it is a very much a normal pH. It is not volatile, and it's safe to use, and it also can be recycled multiple times, though I have not tapped into that in my project. And so we will be using DAS to my defatted seeds in the ratio of 1:10, and after that the supernatant, it will be containing the DS, and we will try to precipitate the protein by achieving the isoelectric point of the protein, which is actually pH 4.5. We achieved it using HCl. And after that we'll add ethanol, because ethanol actually makes the protein coagulate and come together, and then with the help of centrifugation we were able to scrap the protein layer, and we were able to send it for the calorimetric Bradford protein assay. So in that we are using a dye. The dye was Bradford reagent, which happens to be blue in color, which happens to be actually originally in its raw form it will be brown in color, but once you mix it with protein it turns to blue. And then with the help of 595 nanometer we are able to study its absorbance and eventually find its concentration. I would like to conclude with saying, like, it has a lot of future scope. We can since the ratio we are using of DS to defatted seeds is huge, we can try to bring it down. And also we can also try to extract protein from some sort of like processed waste, so that we don't have to tap into our food resources for protein extraction. Again, I would like to say, like, huge thanks to Soumya ma'am and Professor Ethayaraja for offering us this opportunity. It was definitely a very fun course, and which I was very lucky to experience in my final year, and I will definitely cherish this experience forever. Thank you.